Okay, so here we have class 19, and this is example 1, and I'm going to do example 1 and example 3 because it's the same part. And I think I got the thing sorted out, but it was kind of messed up, so this is my second time making this video here. And, all right, so the first thing we want to do is define the center of mass of this piece, and it's made out of plastic. I think that's with the density of 1,000 kilograms per cubic meter, and it's 1 meter by 1 meter. It's like a little L shape that's got a circle cut out of it. So what we do is we want to break it down into fundamental parts. We have a couple choices actually that we could make, but this is the way that I decided to make it. So I made this a vertical rectangle, and then I added a square to it, and then I subtracted out that circle. We could have made it one big square and then cut out a square and then cut out a circle, or we could make it a horizontal rectangle, put a square up at the top, and then cut out a circle. So there was a couple different choices we could make. First thing we want to do is get the masses. So this one right here, they call this part 1 right here. It's useful to number them. And so the mass of 1 is going to be the density of the plastic times the volume, and that's going to be the base times the height times the thickness, right? So that's 1,000 times 0.5 is the base. It's 0.5 wide right here. 1 meter thick, 1 meter tall, excuse me, and 0.5 into the page. And so we end up getting 250 kilograms. For this part 2 over here, he's really half the size. So you would expect it to be half the mass right here. And then for the circle, I actually messed this up right here. This should be that should be r squared right there. Actually, that should be d squared, because it's pi over 4. I use the diameter quite often here. So it would be pi r squared for the area times the thickness. The area times the thickness will give us the volume, and then times the density. So that's what we have right here. Right here, this is actually the diameter squared. So anyway, we get 12.27. And then we get the total mass by adding them up, but of course we consider this to be a negative mass right here, and we find it's 362.7 kilograms. And to find the center of mass, we take the bottom left-hand corner, was just a natural place to take as the reference. We find the sum of the distances to each centroid right here. So this one right here, for mass 1, that's 250 times 0.25 is the x direct, the distance from this reference point in the x direction. And then 125 here, but it's going to be 0.75 is its center of mass. A distance from the reference. And then this last one right here, it was this mass times its distance, but of course it's negative, right? So it's been subtract there. So we divide that whole thing by the total mass, and we get where that distance is going to be. So we notice that it's less than 0.5. If this was a big solid square right here, it would be obviously at 0.5, but we've chopped away at it. We took some material away here, so that shifted the center over, and then also we took some material here, so that shifted the center even further to the left. And the y, we do a similar thing. Now we make sure that we have the 0.5 times the 250, 0.25 times the 125, and 0.25 times that 12.27. Again, it's negative because that part is being subtracted out. And we find that it's 0.4223. Right, so it's again, it's below the midpoint right there, which you would expect because of this large amount taken out. But it isn't as far down because there was some taken out below it, so that would tend to shift it up a little bit. Right. This kind of thing, no, we could do this as an equation, but it really lends itself to making a table. So making the table, you want to make some decisions how big it's going to be. Well, I say how you want decisions how big it's going to be. You can also make a table, as we'll see in the next example or this continuation here on this. I'll just make it into one video. For the table, unfortunately, you can make a table for the center of mass and make a table for the mass moment inertia. And it's like, well, why not just make one table? And yeah, you would actually in Excel, I would make the thing, but it's really hard to squeeze it onto like one page. So like when you're doing it by hand, it's almost often best to just make two tables just because there's just so many columns. Or you can leave out some columns for the things because you can have them as in between steps. You don't necessarily have them. But this is the way that I laid it out. I have the dimensions X, Y, and Z for the pieces of each piece, 1, 2, and 3, and I put an asterisk next to the 3 to try to remind myself that's actually, for that part, is actually being subtracted. So I have the dimensions that I pulled down here, and I made this one is a radius, and whereas the rest of these are X, Y, and Z. And then I also put in where the center distance, the distance from this point is going to be in the X direction, Y direction. And I didn't actually have to do this in the Z direction, so I could have saved that. That's some space I could save. And the volume, now I just take this one times this one times this one times this one for both of the ones that are going to be rectangular prisms, but then this one's going to be different right here, right? Because that's going to be the pi r squared, or the in this case I think I had this is actually should be the diameter, I think, if I had that correctly. And then I multiply by 1,000. Now I could actually put that up as a cell somewhere up in Excel to be so I could change the density if I want to. But I have these calculate these out. There's just the volume times that, and then I multiply each of these masses times dx, dy, dz, so I get these right here, and then I sum up these columns, and here's the total mass, here's the total, you could call this the first moment of inertia, right? It's just mass times the distance instead of the mass times the distance squared, right? So, and then I sum these up, and then I just divide this number by that number, and I get this, and and I call them centroids, because that should actually be the centers of mass, right? Now, because the density is constant, those are the centroids of each of the areas, if you look at them perpendicularly. So it is actually the centroids. But these are the center of masses that we would get. And the Z column, once again, that's not really necessary. That's just being overly thorough. So right here is kind of an approximation of where that's located. Now, when I go for the moment of inertia right here, so here's I'm skipping over the integration examples. For the moment of inertia examples here, we take the I drew this, made it so you could see that it's a three-dimensional thing, and it's actually about Z that we want to rotate it. You could also rotate it about X if you want to, right? So that was the reason why. So that would be like, if this was like, it makes my cell phone is the thing right here, we could rotate it about this way right here. Or we could rotate it about the Y-axis. We could rotate it this way right here, right? But instead, we want to try to rotate it about the Z-axis, the one coming out of the page, right? Rotating it this way right here. Now, we have a choice. If we rotate it about the Z-axis right here, that would be like taking a pin and rotating it like this way right here, rotating the phone about that peak. We would rather rotate it about the center right here, like this right here, right? Where we put a pin right into the center of the thing. Let's see, I don't think I can hold my phone that way, right here, and spin it that way. All right. So you could tell that it'd be harder to spin the thing about a corner than it would be to spin it about the center. So that's the reason why the video is onto the thing, is I was going to hold it up. I should actually 3D print this, right? I should make this thing and 3D print it, and I will. next time. Okay, I'll pass the thing around and actually maybe even make little holes in it or have a way to spin it about it. Actually, that's a really good idea. I like that idea. I'm going to do it. That's my next thing. So anyway, so in order to do this, I'm doing it longhand, but then I'll also make a table out of it. It's a lot more convenient to make it a table. And it's easy to miss some things. So we'll assume that we already got the masses of each of the parts, and we broke them down the same way as we did in the previous example, and we found the center of mass. So the problem asks for it about both ways, right? So actually, let's read the damn problem. Determine the mass moment of inertia and the radius of gyration of the plastic part shown in the figure with respect to the z-axis and the axis passing through the center of the mass that is parallel to the z-axis. So what they mean is this z prime that you see right here, the one in the center where you're spinning it about the easiest axis. It's about its center of mass, the axis that passes through the center of mass that you would expect to rotate this. So we write this out as one long equation. We could say that the mass moment of inertia about the z-axis is going to be the mass moment of inertia about the center of part 1, right? So that's going to be right here, about this point. We're going to only take that rectangle, and then we're going to move it. We're going to move it from here to right here, about the z-axis, right? So you can see that we need to, and here's a big rule. When we're doing things by parts, big rule time. I should have said this in the other video here. Big rule. Remember, in order to add or subtract, you can only do that once you've moved them to a common axis. You can't just add them and then move them, right? You have to move them to a common axis, and you move them with the parallel axis theorem. And because this is like a polar thing, we need this radius dimension. I call it a d here, but it's really sort of a radius that we're moving right here. And then for the second part, that's this square over to the right, we need to get its mass moment of inertia and then also move it. And then we need to subtract out the circle. Well, I put that inside of parentheses there. I have the mass moment of inertia, and then I have what its mass moment of inertia would be after we've moved it, and then I subtract the thing right there. So we look up what the rectangle is, right? And so if I come back to my go to my charts right here. Woo, lots of things. All right, so we go to this guy right here. This is the one we're going to use, and we see that it's 112m b squared plus l squared. That's about the. Let's say that we're doing it about the z-axis, or that's the one that we're showing right here. So we go base times height, right? But each of those squared, not base times height, base squared plus height squared times mass divided by 12. Just a refresher, because we'll need it again. Doing it about the center of a disk or about a cylinder, either one is 1/2 mass times r squared right there. So coming back through all of these, we're right here. Okay, so you see that this is the mass times 0.5 squared plus 1 squared, right? So that's the rectangular one. And then we add in the parallel axis theorem. It's going to be the mass of that part times the distance it moves squared, right? But it turns out that we need to square root 0.25. That's the distance here, and then the 0.5 right here. So we get the square root of that, this distance, but then we're squaring it, right? Because that's that d1 squared. And then we do the same thing for this square over here, right? Of course, with the base and the height are the same. And then we move that also. And now this time, this is going to have a distance that's going to be 0.75 right here. That's the horizontal distance away. And 0.25, that's the vertical distance. Those squared, the square root of those. Oh, by the way, I think I messed up. There needs to be a square right there. That's supposed to be a 2. And then a similar thing. And then you said this one right here, this, I think that's actually a mistake. I think that too needed to be, I probably needed to divide that 0.125 by 2 inside there, right? Because this is supposed to be 1/2 mr squared, and I think 0.125 is actually the diameter. Yes. So there you go. Another mess up. Write that one down. Man, am I full of mess ups. So this, well, actually, that is, oh, okay. So that actually was just, that square was in there. All right, yeah. But this guy right here, he needs to be 2 inside there. I hope the numbers actually work out. But let's check it out. At 179.7. This is going to be a longer video because I'm going to actually do this one in Solidworks just to demonstrate. So the radius of gyration about the z-axis is, okay, so that was the mass moment of inertia about the z-axis. The radius of the radius of gyration is that mass moment of inertia divided by the mass, the square root of it. So 3.995. It sort of gives sort of like a rough kind of like, how is this thing distributed? Another way I think of it is if you had like a disk, what would be like the radius, if you will? I don't know if that's a fair statement here. If you had a radius, not a disk, but let's say that it was, yeah, if it was like a hoop right here, a very, very thin hoop, what would the radius be of that to have the same moment of inertia as the as this thing piece right here? So you would kind of get an idea of how it's distributed. And now if you want the mass moment of inertia about the thing's center of mass, we need to do the opposite of the parallel axis theorem, really. We need to move we need to subtract out from this mass moment of inertia about this z-axis. We need to subtract out the mass times the distance that we have to move, and that turns out to be that x bar squared and y bar squared, the x bar that we got from the previous one. And if we do that, we end up getting 55.44 kilograms times meters squared. And the radius of gyration is now, we'll see that it's a smaller radius of gyration. Of course, it's a much smaller mass moment of inertia right here. So we could have done this as a table. And here's, I tried to make the most concise table. That's true, I got rid of the z's. And so here are the parameters that we already knew from this. And once again, this should be the diameter written up here because that's a 0.125 diameter. And here's the mass. There's the mass moment of inertia. Of course, these are different equations. These two are the same equation. This is a different equation because it's for the disk. And here is the distances from each of these parts that need to move, and you can see that part 2 and 3 have the same distances. That's not true. Yes, no, that's true right there, yeah. And so now this d right here, that's actually this squared, the square root of this squared plus this squared, right? So that's this actual length d. And now we add this mass moment of inertia. We're from add this column plus this mass right here times this squared, and then we add all of those up and we get the mass moment of inertia about z. I calculate this from the previous x bar and y bar. So this is the distance between here and here, right here, that length right there, and I subtract out those things, and this is my, it's a good way to organize the thing. A lot easier to follow, and quite often you would do this in a spreadsheet anyway, so making it in a table works out pretty well. So here you go. I'll see if I can get this to work through. Otherwise, this will be really bad. But anyway, I have remote into my screen at the University of Hartford, and here is Solidworks. So hopefully this will work. So I'm going to create a new part, and that new part, I'm going to change my dimensions into meters. So you can let me do that, hopefully. And I'll go to my front plane, and I'll draw this thing in. Oh, no, I don't want that. I want to draw from a corner. Right, so I'll draw from a corner up, and I will make each side of this 1 meter. There's a lag going on here between me clicking and working. So that's going to make that 1 meter. And this is going to be 1 meter. And I will make this into, I'll extrude this. And I don't think it really matters, but I'll do this 0.25, and I go in the other direction, 0.25. So there's a total of 0.5. And then I will make a cutout of this. So I will take a sketch and grab that corner over there and make this 0.5. Make this 0.5. And you'll see that it's full. It's the sketch is now black. That means it's fully defined. Actually, while I'm there, I could actually have done this in one. It is not going to hurt anything. I will make a drawing line, center line, from the center of this downwards, and that should be 0.25, right? Let's double check that. 0.25, yes, and I'll make a circle that is 0.125. Is it going to be diameter? I think it'll be correct, right? You know, I think I messed up. That's pretty small. Is that what I intended in the others? Let me see. Let me drop back into here proportionally. Yeah, that looks about right, I think. Yeah, okay. It just wasn't too short. Like I thought, I was second guessing myself. So anyway, I take that sketch and I use it as an extrude cut, and I'll just go through all. It'll cut everything apart. And now I need to have define a material. Let me go for. Let me just use the plastic. I don't know what this plastic's density is going to be, but it just made it like a hollow thing right here, but it's interesting. Okay, so let me go up to evaluate, and we will go for mass properties. All right, so in the mass properties thing, it used its default was the density was 1070. All right, so I need to see if I can fake that out and use custom properties here, and it won't let me do that density, huh? That's annoying. This one of the issues I have with my Solidworks account here is that they don't let you change library functions in things. Override mass properties. Yes, that's a good one. Override mass properties, and I will make the mass the same thing. I could even override the mass. So my mass, according to what I calculated, was the total mass was 362, right? So 362.7. All right, so I'm allowed to override that, and we could check this out. And down here is the mass moment of inertia in kilograms square meters. Well, first off, let's take a look at the location of the center of mass right there. Okay, so how did I do on that? By the way, I didn't check these before I did the thing. It's slightly off, actually. I got to wonder about maybe I messed up with the radius versus the diameter of this piece when actually going through the numbers. Got to double check on that. So I might have messed that thing up when going through there. Okay, so actually this shows right here that the density, I might have messed up the volume of this, right? Because I told the thing that it had to be this amount right here, but the density should be equal to 1,000 right here. So there is a numeric mistake in here. Damn. Would have been much more impressive. But anyway, the center of mass right here, and by the way, this is totally normal. This gets messed up, like so easy to make simple mistakes in this type of function. This is engineering the pitfalls. But one reason why you want to check things, right? You do a calculation. If you can find another way to do it, in this case, I made a model out of it. And anyway, so I have 0.405 was what I got for here, but it shows it as 0.4112. And then 0.422 is what I got on page, but it's 0.41944, so there's a mistake somewhere. But if I go and I take a look at the moment of inertia, you could see that this guy right here was about the center of mass, right? So taking about and aligned, taken at the center of mass and aligned with the output coordinate system, that would be Z. I have 55.47 in my model here. I had 55.51, and I'm sorry, not my model, but in my calculations. And then again, my first answer for the moment of inertia about the z-axis was 179.7. Here I get 180.5. So it wasn't completely successful. I demonstrated a pitfall of doing this in and not being very, very careful, and I should have been very, very careful. But now I've made a 26-minute video, and you're supposed to keep these short, but I didn't do it. So here is some more guitar. Here's my Les Paul Standard, right? Black. I love black guitars, and I changed the hardware out to be black. Do I have my? Looking around, I have a signed pick guard from Les Paul. I don't know where that went. Anyway, it's usually sitting right over here somewhere. I'll find it. But that's kind of cool, right? You don't even know who Les Paul is, but he was a famous. Here it is. Right here. So this is the pick guard that usually goes on to this guitar, but he says, "To Ted, keep picking, Les Paul." Right? Les Paul passed away a number of years ago, but I did see him at the Iridium down in Manhattan. That guy, he was like 83 years old, and he was playing. But this is a Les Paul model. But Les Paul was playing jazz and kind of fun, kind of 1950s music, kind of musician, but never intended it for be the heavy metal guitar of choice. For one of the most classic guitars that exists is the Gibson Les Paul. But Les Paul as a guy, he was a great entertainer. What an entertaining guy. That's not really my taste in music, but man, did I enjoy listening to him play. So that was your guitar lesson for today. Thank you for paying attention, and hope everyone's safe and secure.